You ever look at one of your smart devices, maybe a light bulb you control from your phone, and just wonder, how does that actually work? It really feels like magic, right? Well, behind every bit of that magic, there's code. So today, let's pull back the curtain and see how that code gets onto a device and makes it come to life. I mean, take this smart plug. It's so simple. You plug it into the wall, you download an app, and boom, you can turn your lamp on from across the country. For you, the user, it's dead simple. But how did that little plug get its instructions in the first place? That's the rabbit hole we're diving down today. And there's a world of difference between a consumer gadget like that plug, which comes all set up for you, and a custom project where you're the one doing the programming. We're going to explore what it takes to make that jump, from just using a device to actually creating one. All right, so before you can build anything, you need a workbench, right? A place to lay out your tools. Well, for programming an IoT device, it's the same idea. You need to set up your digital workbench. This is where all the real work happens. And you can think of this workbench as having kind of 3 levels of power. We'll start with the most raw, direct way to talk to a computer, the command line. Then we'll check out a simple text editor for just writing code. And finally, we'll look at the all-in-one powerhouse, the integrated development environment. So, the command line interface, or CLI. This is where it all started. Way before you could click on shiny icons with a mouse, this is how you told a computer what to do, by literally typing in your commands. Whether you know it as command prompt or terminal, it's your direct line to the machine's brain. Okay, so the next step up from that is the good old text editor. Think of it like a super focused, distraction-free notepad. It's not for writing essays, it's designed for one thing and one thing only, getting your code, your instructions written down cleanly. But when you're ready to get really serious, that's when you graduate to an IDE. This is the pro-level setup. It's an all-in-one workstation that takes that simple text editor and wraps it in a whole suite of amazing tools that make writing, finding mistakes, and testing your code 1,000 times easier. So what makes an IDE so great? Well, it's features like these. Imagine your editor just knowing what you're about to type and finishing the command for you. Or what if it color-coded everything to make it super easy to read? And best of all, it's like having a grammar checker for your code that points out your mistakes the second you make them. Let's zero in on that syntax highlighting for a second. It's not just to make the code look cool. By giving different parts of your code different colors, it adds meaning. It helps a developer see the entire structure of the program at a glance, making it so much faster to spot if something's out of place. And this right here, this is every developer's best friend. Seriously, error highlighting. You see that angry little red squiggly line? That's your IDE yelling, "Hey, something's wrong right here," before you even try to run your program. This feature alone saves an unbelievable amount of headache and time. All right, so you've got your workbench set up, you've got your tools. Now what? Well, you need a blueprint. And in the world of programming, your blueprint is the language you choose to write in. And for IoT, that choice is absolutely critical. And here's why you can't just pick any old language. A lot of these IoT devices are tiny, and they're running on battery power. So your code has to be super efficient, it needs to be portable to run on different kinds of chips, it has to sip power, it needs to be flexible enough to talk to hardware directly, and it still has to be readable for us humans. So let's break down some of the heavy hitters. You've got Java, which is famous for its whole write once, run anywhere philosophy. Then you have C and C++, the old school workhorses that give you incredible efficiency and control over the hardware. After that, there's Python, which is just fantastic to read and amazing for projects that crunch a lot of data. And you know what? Even JavaScript gets in on the action, especially for tiny, low-power devices. Okay, so we've got our tools and we've got our blueprint. The last piece of the puzzle is learning the grammar. Just like English or Spanish, programming languages have rules, a structure you have to follow so the computer can actually understand what you're trying to say. And here's the key thing to get. Every instruction you write is basically a sentence. You've got the command, which is your verb, the action you want to perform. You have options, which act like adverbs, changing how the action works. And you have arguments, which are the nouns, the things you're performing the action on. Let's look at a super common example, ls-al. Here, ls is the command. It means list stuff. And the -al part, those are the options or flags. They tell the ls command, hey, don't just list stuff, I want you to list all the files, and I want you to do it in a long, detailed format. See? Action and then controls for that action. Now, here's a secret. Nobody, and I mean nobody, writes all their code from scratch. That would be insane. Instead, developers rely on libraries. These are just pre-written bundles of code that you can plug into your own program to give it new powers. In Python, they're called modules. They're like specialized toolkits for your project. Okay, so let's play this out. Imagine you're trying to control the hardware pins on a Raspberry Pi. You'd write a line like import rpi.gpio to bring in that specific toolkit. You run it, but bam, you get a big fat error, module not found. Your program just crashed because it can't find the toolkit you asked for. And this happens to every single developer, all the time. You know you need a specific tool, but it's just not on your workbench yet. So what do? How do you get it? Well, for Python, the answer is a neat little tool called pip. Think of pip as an app store, but for code libraries. It connects to this massive online warehouse of free toolkits and lets you download and install whatever you need with just a single command. And just like that, the solution is so simple. You just go to your command line and type pip install rpi.gpo. Pip goes out to the internet, finds that library, downloads it, and plugs it right into your workbench. Now, when you run your program again, the error is gone. It just works. So, what are these tools inside the toolkit we just installed? Well, in code speak, they're called functions or methods. They're the specific actions the library lets you perform. You call them using a dot. So when you write gpio.setup, you're basically saying, hey, from that GPIO toolkit, I want to use the setup tool right now. All right, let's zoom out and put all these pieces together. We've looked at 3 different layers: the tools you build with, the blueprint you follow, and the grammar you use to write instructions. When you combine all 3, that's where you get to build your own magic. So, when you boil it all down, the process is pretty straightforward. First, you grab your toolkit. You set up a powerful IDE. Then you choose your blueprint. You pick the best programming language for the job. You follow the rules of grammar, using commands, libraries, and functions to write your instructions. And when you put it all together, that's how the magic happens. So you see, that magic inside your smart plug? It's not really magic at all. It's just a clever combination of the right tools, a well-chosen language, and a clear set of instructions. So, I guess the only question left is, now that you know the recipe, what will you create?